Suppose we have an ideal battery with an EMF of 12 volts and a circuit that includes a capacitor with capacitance, we'll say 80 millifarads, and a resistor whose value we'll set at 3,000 ohms. The capacitor is initially uncharged, and we throw the switch into position A. Now you know that means we create a dead branch here in the circuit. Well, what would a graph look like for, how about all three of these voltmeters? Let's put a voltmeter in parallel with the capacitor. Let's put a voltmeter in parallel with the resistor. And let's put a voltmeter in parallel with the battery. We could graph all three voltages as functions of time. So the voltage across the resistor as time passes by. Now we know there's a value we call the time constant, represented by the Greek letter tau. It's equal to the product of the resistance and the capacitance. I think we've shown in a previous lesson that multiplying farads times ohms indeed gives units of seconds. Anyway, this value of tau represents the time that it takes for the charge on the capacitor to reach 63% of its maximum value. Another way to say that is it's the time that it takes for the current in the circuit to reach, or I should say to drop, to 37% of its initial value. So also, let's imagine we have an ammeter in this circuit as well. So we would have to break the circuit open at some point. So I don't know, we might as well choose right here as the spot to break the circuit open. Just as long as we put this anywhere along the loop, but that point's as good as any. So there's our ammeter. So maybe we make a graph of the current versus time as well. But anyway, let's start with the voltage across the resistor. Well, because this current starts out at an initial value, and by the way, the initial value of the current is nothing more than the EMF of the battery divided by the resistance in the circuit. So in this case, it would be 12 volts divided by 3,000 ohms, or what? If it was just 12 divided by 3, we would call it 4, but we're dividing it by 3,000, so how about we call it 4 milliamps? Okay, as time goes by, that current ultimately is going to drop to 0, right? At some point, our capacitor is going to be fully charged, meaning the positive charge on the upper plate and the negative charge on the lower plate will be equal to one another, so the net charge of the capacitor, like all capacitors, will be 0. But the magnitude of charge on either one of the plates will reach the greatest value it can possibly be. Now what is that value? We call it Q max. We know that's equal to the capacitance multiplied by the EMF of the battery. Once the charge reaches this value, there's no longer any current in the circuit, and the ammeter reading goes to 0. So the ammeter is going to start with a reading of 4 milliamps and drop to a reading of 0 as the charge on the capacitor goes from 0 up to this maximum value. Now, how do we determine voltage across a resistor? That follows from Ohm's law. V is equal to I times R. Now, I'm not going to write capital I times R because capital letters typically signify constant values, and what we're saying here is the current is going to vary with time, so I'll use a symbol lowercase I. So if the current starts out at some maximum value and then drops towards 0, that means the voltage across the resistor has to start out at some initial maximum value and drop to 0. Yeah, so there we finally have what we can predict the shape of the graph would be for the reading on the voltmeter that's connected across the resistor. Now, what is this initial value? It's the initial current multiplied by the resistance, which we agree is 4 milliamps, and we multiply 4 milliamps times 3,000 ohms. Well, the milli and the 1,000 can cancel out, and 4 times 3, well, no surprise, that's 12 volts. In other words, the voltage across the resistor is the voltage across the battery. Now, does this agree with Kirchhoff's loop rule? Let's pick a point here. We'll call it point P. As we trace our way around the circuit, voltage gain has to equal voltage loss. Okay, so we just gained 12 volts as we go from, how about choose a different color that shows up better? Yep. We've gained 12 volts as we go across the battery. We continue through the switch. Now, as we go across the capacitor, there's no voltage gained or lost initially, meaning immediately after the switch is thrown into position A, because there's no charge initially on the capacitor. And if there's no charge, there's no voltage across it. So there's 0 voltage drop across the capacitor, and all the voltage that was gained across the battery is then lost here across the resistor, right? If we were to state Kirchhoff's loop rule mathematically, we would say the voltage gained across the battery minus the voltage lost across the capacitor minus the voltage lost across the resistor is equal to 0. So initially, this is 12, this is 0, this is negative 12, and so it all works out. Now, as time goes by, we'll say, not after a little time goes by, but as time approaches some infinite value, we'll refer to that as the steady state. The circuit ultimately is going to reach some steady values of charge across the capacitor. There's going to be a steady value of current in the ammeter. By the way, that steady value will be 0, right? In any case, that's the terminology we'll use for what happens to the circuit after a long amount of time has passed. It reaches a steady state. Well, in the steady state, the voltage across the battery is still 12, and then all of the voltage is across the capacitor, and there's no longer any voltage across the resistor. So the role of voltage across the capacitor and resistor are reciprocating as time goes by. This is a voltage divider circuit, right? You remember the voltage divider that was presented in an earlier lesson, made of a battery and 2 resistors connected in series. Well, here we have this first resistor replaced with a capacitor. But the rules for a voltage divider still have to hold up. According to Kirchhoff's loop rule, the voltage across the capacitor plus the voltage across the resistor at any instant in time have to equal the voltage across the battery. Okay, so on the same set of axes then, I guess we can also graph the voltage across the capacitor. So how do we calculate voltage for a capacitor? Let's consider the most basic equation for capacitors. Charge is equal to the product of voltage and capacitance. So voltage is found by dividing charge by capacitance. And we know the charge starts out at 0, and it takes an infinite amount of time to reach this maximum value found by taking the product of the capacitance and the EMF of the battery. So this voltmeter that's connected in parallel with the capacitor is going to start out with a reading of 0 as the capacitor is initially uncharged, and then as time goes by, it asymptotically grows to equal the voltage across the battery. So where's the value of tau on this graph? Remember that tau represents an amount of time, and our x-axis is the time axis. So I believe tau would probably be about here. Why did I choose this point? Well, it looks about right. If I were to read up and across, then it looks like this point might represent 37%, and if I read up, this point might represent about 63%, right? Now, notice we could choose any random point in time. How about right here? Then we'll just call that lowercase t. It's not a special time that we might represent with this Greek letter tau. This is just any old variable amount of time. If we take the voltage across the resistor and the voltage across the capacitor at that instant in time and add those values together, what does it add up to? Yeah, it's always going to add up to, in this case, 12 volts, or in other words, the EMF of the battery. This time is one interesting one where the two curves intersect. That just happens to be the moment in time where both the capacitor and the resistor would have a value of 6 volts across their terminals. Okay. Oh, by the way, then if we graph the battery voltage, how about we color code all this? Let's go with green for the voltage across the battery. So let me graph that. There it is. That's just always going to read 12 volts. Let's go with, how about purple? Oops. Pink. Okay, so the voltage across the resistor, well, we've already graphed that. That's the one that starts out at some maximum value equal to the battery voltage and asymptotically approaches 0. And then, how about we pick blue for the voltage across the capacitor, and we've already graphed that. Okay, so there we have it, the graphs of all three of these voltmeter readings, the battery, the resistor, the capacitor, and we can see Kirchhoff's loop rule holds true in the case of this circuit. But what about the graph of current versus time? Yeah, if we graph the reading from the ammeter as time goes by, well, that graph really is going to have the exact same shape as the graph of the voltage across the resistor, because keep in mind, the voltage across a resistor is equal to the current through the resistor multiplied by the resistance of the resistor. Well, that's a constant value, and so as goes the current, so goes the voltage across the resistor. So this starts out as 12 volts divided by 3,000 ohms, which we agreed is 4 milliamps. So where is tau on this graph? Right here, the product of R and C. So if we were to read across, this represents 37% of 4 milliamps. So just a reminder of what our circuit looks like with the switch closed. It's just a battery in series with a capacitor and a resistance. In this case, we have a time constant of 3,000 ohms multiplied by 80 millifarads. I can cancel out 1,000 and milli, because milli means a thousandth, right? So easy mental math here, 3 times 80 gives us 240. 240 ohms farads, well, that's 240 seconds. which, by the way, would be equal to what? 4 minutes. So what does that 4 minutes represent? The time that it takes for the capacitor to become fully charged? No, it takes an infinite amount of time to be fully charged. 4 minutes represents the amount of time it takes to reach 67% of its maximum charge. Now, what is that maximum charge? That's found by multiplying the capacitance times the battery voltage, 12 volts, 3,000 ohms, 80 millifarads. So when we multiply 80 millifarads times 12 volts, well, let's see, that would be, 960 millicoulombs. So just short of 1 coulomb of charge develops on either one of the plates after an infinite amount of time. So after the time is equal to the time constant tau, which is the product of R and C, which in our example is 4 minutes, then the amount of charge is equal to 63% of 960 millicoulombs, which would be equal to, got to reach for my calculator, which would be about 605 millicoulombs. So we could ask this question: how much time would it take for the charge across the capacitor to be equal to exactly 1/2 of a coulomb, or 0.5 coulombs? Well, the charge is equal to the maximum charge times the quantity 1 minus e to the negative t over tau. We derived that in a previous lesson, the lesson on charging a capacitor. So 0.5 times the maximum charge is equal to the maximum charge times 1 minus e to the negative t over tau. Now we can cancel out maximum charge, and we have, let's see, we'll bring this to this side of the equation. We'll bring the 0.5 to this side of the equation. We have e to the negative t over tau is equal to 1 minus 0.5, which itself is 0.5, which we could call 1/2 if we prefer. And then we can take the inverse of both sides of the equation, 1 over, 1 over. So now we have e to the positive t over tau is equal to 2. Let's take the natural log of both sides. Then we have t divided by tau is equal to the natural log of 2. And so the time it would take for the charge to be half of its maximum possible value is the time constant tau multiplied by the natural log of 2. So that's 4 minutes, or 240 seconds, multiplied by natural log of 2. Which gives us about 166 seconds, or if you want, 2 minutes and 46 seconds. So again, we look at the graph of charge versus time for the capacitor. Initially, the capacitor is uncharged, and it takes a time of 4 minutes to reach 63% of that maximum value charge, which, by the way, happens to be equal to, as we said, 960 millicoulombs. So where does 2 minutes and 46 seconds plot out? Right here at exactly 50% of the maximum charge. So just a little insight into the different values that we could measure for the components of this circuit, the voltage across the capacitor, the voltage across the resistor, the voltage of the battery, all of those graphed here, the current in the circuit graphed here, the charge on either one of the plates of the capacitor graphed here. All right, thanks for watching.